right? Everybody look into it. So the last part of this topic is about tri substitutions, or we can say it as multi-group substitutions. So in case if you have these kind of groups where one of them is donating group, we can see this is electron donating group while chlorine is electron withdrawing. Okay. And then you are making a bromination on it, right? In such case, what we do, we have chlorine here, right? And now I need to accommodate this bromine. So we will place the bromine as per the direction of OH, because generally we learned that when it comes to rate of EAS, the group which is present on benzene, if it is electron donating group, that would have more priority as compared to only benzene, or as compared to electron withdrawing group. So within the group, if you notice, OH is more donating and it will keep ortho and para more activated. Out of this, because para in general is more major quantity, so we can get bromine here and one bromine here. This will be major, this will be minor, and of course there is one chlorine which is still present on this position like this. So what did we learn from here? I'll put it as a note. Got it? That is, if you have donating and withdrawing, note, if activating and deactivating, if activating and deactivating groups are present, then prioritize prioritize activating groups for EAS. Done. Next, second case. Now in this case, you notice that both of them are deactivating. Clear? So what if you have chlorine? You can notice that chlorine is deactivating, right? And NO2 is also deactivating. Okay. In such case, if these two are deactivating, the one which is at least orthopara, which is less deactivating, in this case, the less deactivating is chlorine. The one which is less deactivating, always listen to that first. So which means, let me put this NO2 and NO2 the way it is. And now, based on this, we need to notice that whether we have to go for ortho, and this para is open. Okay, ortho, and para is open to us. So go with the para position of chlorine, because generally para is major. So hence you will see bromine here and bromine here, right? These two. Of course, there is the third one where bromine is here, but that is much lesser in quantity. So this one is major compound, this one is minor. Got it? Next, if you have three substitutions, out of which even if one of them is donating, that is one of them is activating, you'll always listen to that first. Always go with the activation part. Hence, you will keep this NO2 the way it is, Cl the way it is, but make sure that the bromine will be listened to CH3. That means you go as per the CH3 group. Next, I have one ring which is deactivating, one ring which is activating. So always listen to the activating part. So bromine will come here, bromine will come here, keeping the chlorine intact at the same position. Hence, this will be major and this will be minor product. Right? This is what we need to learn from, activating and deactivating cases. Clear? So I think this part is understood to everybody. Okay, how we need to check out these cases. Right. OP ratio, we have learned this already, but this time for toluene cases. In case if you have toluene, then what will be the OP ratio? Okay, see, in case of toluene, if you make chlorination, specifically chlorination, through EAS mechanism, then you can get ortho and para. But usually we get para as major, but not in this case. In this case, you will find ortho as major. Ortho is slightly greater than para, specifically when you do chlorination as well as nitration. See, it comes with the fact that methyl will always give you, methyl will give us plus psi effect as well as hyperconjugation. Hyperconjugation makes the resonance activated on ortho and para position. But plus psi will always give more priority to the closer distance. In this case, it is ortho. That's why ortho is getting more priority. Specifically in the case of chlorine and HNO3, it will give you ortho substitution more than para substitution. Clear on this part? Right. Okay. This was a JE question which was asked last year. See, we have OH and CH3. Then we are doing Friedel-Crafts acylation. We are trying to perform Friedel-Crafts acylation. Friedel-Crafts acylation is observed only in the cases where we have weak donating or weak withdrawing. Not observed in the case of strong donating or strong withdrawing. So OH is very strong donating. So don't listen or don't think in terms of OH, but think in terms of methyl. Okay. So with respect to methyl, if you compare, this is ortho, ortho and para. According to that, on the para position, acylation will happen and ortho position acylation will happen, and this will be minor product. The other one will be major product. Got it? Sulfonation. For toluene, if you make sulfonation, you will get ortho para as major product, ortho as minor product. This is how typically it will happen in normal sulfonation cases or alkylation, acylation in all those cases, except in the case of chlorination and nitration. So please do remember only these two cases you will have ortho is major than para, rest all cases it won't be. Clear? Now, if you ask me as much as theory is concerned, correct, these are the terms you need to know, correct? Apart of it, there are few, extra points that you need to learn. Okay, these are like by chance if it is asked. Okay, so those kind of cases, let us focus on that. Correct. This I haven't written in the regular notes. I usually, do it only, uh, and I feel like okay, this point we can again discuss it later. So check it out. One such point is we have carbonation on benzene. Okay, so first reaction. These are all extra points. Extra points. So first one being okay, carbonation. Got it? So see, when it comes to carbonation, which means it is reaction of carbon dioxide with benzene. Carbon dioxide with benzene. Okay? Clear? One second. So see, what's happening here is benzene will try to react with carbon dioxide. Carbon dioxide naturally has sufficient delta positive charge on it, like this delta plus and minus, because of which it can act like an electrophile. To facilitate it better, we can use AlCl3 and a little bit of heat that will help it to make the reaction much easier. So that means the benzene will go attack on C double bond O, that converts into C double bond O and O minus. And that on hydrolysis, I mean, of course, we have AlCl4, AlCl3 here, this way, with plus, sorry, Yeah, this minus will be appearing on AlCl3, my mistake. And then on hydrolysis, you will get this as COOH. That's how we can get COOH group. Okay. So benzoic acid is what you will get, and AlCl3 will be left over. Second such reaction is, oxymercuration. Oxymercuration. We have come across this oxymercuration in the case of alkenes, right? Overall reaction is like this. When you have benzene, you could imagine a similar type of addition how we did it in alkenes. So we will get this as, just a second. Right, sorry. Take out. In the case of oxymercuration, we have HgOAC twice. This is the uh, mercury acetate salt. This on hydrolysis, correct, will give us benzene with HgOAC. Okay, this is what you will get. Now, this is basically a reversible reaction. Okay, this is reversible reaction. Okay, actually, usually when you have reversible reaction, they shows, I mean, or they will show primary isotopic effect. Primary isotopic effect. So primary isotopic effect is observed. All right. Of course, I can go through mechanism, but I don't think mechanism is something which is required here. So I would suggest just don't worry about it. Just remember the name reaction, what it is. Similar reaction we have, right? So which is phthalation. Okay, so basically we have thallium being added, so that's why it is called phthalation. So benzene, if you react with thallium, correct, which is again connected with this acetate, fluoroacetate group CF3COO thrice. This will also exist in equilibrium with thallium part, which is TL, CF3COO twice, and the hydrogen which is left will convert into CF3COOH. So this is the electrophilic substitution which you will get. Clear? Usually, phthalation is best used because once you get this intermediate, it becomes very easy to replace that with fluorine. So that's why it is usually always backed up with this reaction where you have K plus and BF4 minus, by which you can remove the phthalic form here and you'll get F here, and we will get this TL CF3 COO twice, correct? And the F minus will go away and this will come out as minus and K plus like this. Okay, we will get this fluorine form. Got it? The idea is the same, everybody. Once again, right? So I hope all of you got that. Right. Next, these are all the extra reactions from benzene's point of view. Now, we have reactions of benzene, toluene, as well as naphthalene. We have seen phenol, amine, but extra reactions that could be asked is about pyridine. So think the benzene reactions similar to that of pyridine, and then we see what are all the reactions we can offer. So we can see pyridine, pyridine, EAS reactions. So what are all the pyridine EAS reactions? See, starting with N here, this is pyridine, and if pyridine has to make different reactions here, so starting with first Friedel-Crafts acylation, that is R C double bond O Cl in the presence of AlCl3. Now that will undergo acylation. You know that in case of pyridine we have alpha, beta, gamma, and we know that beta is most stable form of the intermediate here. So you should always write it at beta position. Okay. Similarly, if you have to do nitration here, so typically the nitration is done by this. So we have Bf3, correct? Sorry, Bf4 minus and NO2 plus. Correct. So by that you will get NO2 substituted at this position, nitration, and bromine and bromine substitution is very similar to how we do it on benzene here. So we will get Br getting substituted here, correct? Chlorine also in the same way, mostly used with Cl2, AlCl3 anhydrous. So this will give you chlorination on pyridine. This way you can get chlorination form. Alkylation can also be, Friedel-Crafts alkylation can also be done just like acylation, right? So we can get Rx, get R, Cl in the presence of AlCl3. So that would give us substitution at this R position here. Okay. So these are typical pyridine reactions, everybody. So they are very, very similar to that of what you get it otherwise. Okay. Now, next we learned naphthalene, but certain important cases of naphthalene. Check out important cases of naphthalene. That is, in case if you have naphthalene here like this, and we know that generally if you do bromination or halogenation or alkylation, we will get that ortho position which is major, correct? But now it also depends upon temperature. In certain cases, it also depends upon temperature. So that's why, in case if you are doing a nitration using concentrated HNO3 and concentrated H2SO4, but you're operating this at 80 degrees Celsius. Got it? So in that case, we will add at uh, alpha position here. Okay, just a second. Right. While if you operate the same thing, correct? If you operate the same thing, right, with concentrated HNO3 and concentrated H2SO4 at around 160 degrees Celsius, in that case, we will get NO2. Okay. So we will get, at high temperature, you will get it at para position. Now the same logic applies even if you take it in the case of sulfonation. Right? So that means in case if I take sulfonation, so just remove this part, that's it. So now it will go for sulfonation part. Okay. So if you do the sulfonation part also, you'll get this as SO3H here and SO3H here. This is called thermally controlled product. This is called kinetically controlled product. This is kinetically controlled product. Okay. So remember, alpha part is kinetically controlled and beta part is thermally controlled. Okay. Clear? Now, if you have it, forgot. Sorry. Yeah. One more case. In case if you have alkylation and acylation being done. Okay. So usually in the case of acylation here, right? In the case of acylation, that is, in case if you have RC double bond OCl, okay, this with AlCl3 in the presence of CS2, that is non-polar solvent, then you will get this at alpha position. But if you do the same thing, RC double bond OCl with AlCl3 in the presence of nitrobenzene. See, nitrobenzene is polar now. So this is polar. So when you put it in polar form, then you will get this at the beta position. This is non-polar and this is polar. So please do remember it like this. You don't have to analyze so much about why that will happen, but just observe it. If it is given as polar and non-polar, accordingly you substitute them. So this is the drill assignment. You can see one by one. What are the products here? First, N-hexane to benzene. Okay, so we learned that we need to use Cr2O3 or Al2O3 combined with a temperature at 773 kelvins and around 20 to 200 atm pressure. So this is, or we can use MO2O3, same temperature, 773 kelvins. Okay, or sorry, one more thing. No, no, only these two reagents. Okay, Cr2O3, Al2O3 at this temperature or MO2O3 at 773. Next, if you already have a cyclohexane, right? In that case, we can simply use selenium, sulfur, or platinum and heat. That's it. And the same thing can be done even if you have an alkene also. All of you please try to recall that. This is all we have done it through the part of notes now. Next, if you have bromine and I want to convert bromobenzene and I want to convert into benzene, first I need to use Grignard's reagent RMgX. That way I will be able to get this as minus with, sorry, not Grignard's, I meant to say Mg. We have to prepare it as Grignard's reagent. So Mg plus Br minus, like this. Okay, Mg plus. Okay, once you get this one and using hydrolysis, so this plus, once you get this part, then follow that with hydrolysis, you will get benzene. Okay, because this minus part will take H plus, the phenyl anion will take H plus and convert into benzene. Second, phenol to benzene, we have only one reaction, zinc and heat. Zinc and heat will give you benzene and ZNO. Diazonium salt to benzene, we have two reagents. One is H3PO2 or we can take ethanol, right? In this case, this H3PO2 will convert into H3PO3 or ethanol will convert into acetaldehyde. That these will get oxidized and here N2 gas will go away and hydrogen will come here. That's how we can get benzene. Carboxylic acid, we learned that we can use NaOH and CaO, which we call it as soda lime decarboxylation, through which we can get benzene. Next, sulfonic acid, we learned that either we can use simply steam and heat, or we can simply use dilute H plus. So it is a desulfonation reaction. It's a reverse reaction. So we will notice that that SO3H will go away and you will get this as benzene form. So please check the preparations quickly. If everybody has got this, any doubt with it, these are the reagents which you need to know. Done? Right. Now see the product formation. Benzene with bromine, bromobenzene. So we'll get bromobenzene, correct? Here we can get chlorobenzene. Now in this case, which is an electrophile, iodine, because chlorine is more electronegative, so iodobenzene. HOCl, in this case, Cl plus will be the electrophile, so Cl, chlorobenzene. Iodine in NaOH. Acha, iodine NaOH, do we, it will get oxidized to IO plus and, sorry, IO minus. See, first remember, any halogen, we discussed this multiple times, in the presence of NaOH, it will get converted into NaX plus NaOX, right? This NaOX in hydrolysis in water, it can be converted into HOX, and this HOX will have H plus and OH minus part. So basically here we'll have this X plus. So that means here we'll have iodine plus. Hence, we can write that as iodobenzene again using this also. This is also iodobenzene. In fact, HiO3, why it is being used? Let me write on that. HiO3 is used as mild oxidizing agent. Used as mild oxidizing agent. Hmm. Concentrated H2SO4, sulfonation. Concentrated HNO3, nitration. Uh, AlBr3, Friedel-Crafts alkylation. So we will get this as methyl here. Next, this one, when you use ZnCl2, this is called Gattermann-Koch reaction. Gattermann-Koch, let me remind you again with the mechanism. Everybody, I'll write a bit of mechanism also here. So we have H, C, double bond O, H here. And that when you treat with HCl, like this, in the presence of ZnCl2. So chlorine will connect here, lone pair will connect here, bond will break here. So basically what you're getting here is CH2O H with a plus charge on carbon with ZnCl3 minus. This is Cl2. Okay. This is the way you will get. So carbon has a positive charge on which benzene will attach. Hence, that will convert into CH2OH. Okay. Clear? So basically, it's an alcohol formation. It is very similar to Gattermann-Koch reaction. In Gattermann-Koch, basically, instead of taking HCHO, we take carbon monoxide. That's the only difference. When you take carbon monoxide here, it will convert into an aldehyde. If you already taken formaldehyde, right? So then this is called, this will convert into methanol. Okay, next. H2. PtO2 is called Adams catalyst. In the presence of Adams catalyst, the double bonds inside the benzene ring will get reduced. V2O5, if you are heating at 300 degrees, it will convert into phenol. If you go for a higher temperature, it will convert into an anhydride, maleic anhydride. So this is maleic anhydride. Okay, maleic anhydride. Right. Next, this one. This is Gattermann formylation reaction. This is Gattermann formylation. So basically here Cn minus will take H plus from here, and on that carbon benzene will attach. Thereafter hydrolysis will happen. So you will get aldehyde. So the name is Gattermann formaldehyde or formyl reaction. Next. If you take carbon monoxide, just now I told you what is the reaction name, Gattermann-Koch. Gattermann-Koch. Next, if you have POCl3 here, so reaction type is same here. NMe thrice will go away from here. So you will get again similar reaction. You will get this as an aldehyde. Okay. So just like how here nitrogen left, here NMe3 will also leave, leaving behind the formaldehyde form. Next, D2SO4, excess amount of deuteration. Deuteration will happen at all the positions. You will get D, 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 and D at all positions. Next, chlorination. See, if you haven't mentioned anything excess also, if you haven't mentioned one equivalent like this, then you will take that sufficient chlorination is happening and you go for addition reaction. So all of them undergoes addition reaction in a radical mechanism. So this is a radical mechanism. It will go addition. So we'll get C6H6Cl6. Okay, which we call it as benzene hexachloride. The industrial name for this is gamaxine. This is gamaxine. So remember, you will get gamaxine. Next, chlorine, if you take excess, so we will get this as only EAS reaction this time. Via EAS mechanism, all the chlorines will be substituted. So this is what we call it as, we will get this as C6Cl6 HCB, hexachlorobenzene. So this is a difference between BHC and HCB. Okay, HCB is used when you have hexachlorobenzene, correct? And BHC is benzene hexachloride. So there is a slight difference between these two. So quickly go through all the reactions once. So first I'll give you reactions up to this. Please make a note. If not, if you don't have the sheet, please at least make sure you know the product, write down the products for all of them. Let me, let me remind you what is Birch reduction. Birch reduction was carried out in alkynes. That is C, triple bond C, some R dash is there. And this, if you react this with liquid, sorry, if you react with lithium in liquid ammonia or sodium in liquid ammonia, we used to get this as a double bond because reduction would happen here in this form. C, double bond C, some R dash, we'll get H and H. So what we are getting is a transalkene. Transalkene. This was the whole purpose of the Birch reduction. In fact, Birch reduction was also observed in the case of alternative double bonds, correct? So, I mean the cumulative double bonds here, conjugated double bonds here, sorry. So that when you react, we used to get double bond here with hydrogen and hydrogen forming at these two locations. Again, sorry, it is in the trans form, like this in a trans form. So addition happens at 1 and 4 position, correct? The same thing happens even on benzene also. So if you have benzene here with lithium in liquid ammonia, we will get 1 4 addition here also. So we will get 1 here, 4 here with double bond and double bond. So just to recall you about the mechanism, how it happens, lithium lithium or sodium, both releases electrons, and these electrons will go and combine on one particular location here, by which this pi bond will move and you will get minus charge here and a single electron species here, radical form. The whole point of Birch reduction is to keep these electrons as far away as possible. Through resonance, you will see double bond can be pushed here and lone pair electrons can come here. Single electron can be here. Now they are far away from each other. Once they are far away from each other, that's when it will react with ammonia and then takes away that H plus. So we'll get H here, double bond, and single electron. And now this single electron, which is in a radical form, correct, will take one more electron to that, convert into a pair of electrons. So like this, with a pair of electrons, and that plus NH3 will be converting that into H and H here with double. That's the mechanism. Okay. Now this is for benzene. Similarly, if you notice, by chance, if you have benzene with an electron withdrawing group, let's say like ester is a withdrawing group. In that case, if you react with lithium and liquid ammonia, any withdrawing groups on benzene, then you will get an addition like this. So COOR, H will get added, H will get added. While if you have any donating groups on it, like CH3, which is a donating group, and if we are treating that with liquid and lithium and liquid ammonia, then the addition will happen such a way. Now the double bond will be here like this. Okay, sorry, like this with CH3. So addition happens at these two ends now. Correct? This is the way it will happen. So remember, for withdrawing groups, the pi bonds will be vertical. For donating groups, pi bonds will be slanted. Two pi bonds will be slanted. Okay. So this is the idea you need to have about burst reduction, everybody. Got it? Likewise, there is one more reaction that you need to just know about it. We don't have to go much details into it right now because we will be repeating this once again. So that is Etard reaction. The entire mechanism will also be explained to you in aldehydes and ketone topic as of now, because it's a part of benzene reactions. I'm just mentioning that here. So in case if you have chromyl chloride, that is Cr2Cl2 with toluene. So toluene basically, makes a combination with chromyl chloride as CO, Cr, Cl2 and OH twice. 2 moles will attach like this. And then on hydrolysis, those two groups will go away, converting that into an aldehyde group. So that's how we can get an aldehyde form. This is called Etard reaction. An alternative reaction is that CrO3 in the presence of anhydride, that is CH3, C double bond O, C double bond O, CH3. This will also make it in a very similar type. We have CH, we will get OAC and OAC as the two groups connected on it here. And then on hydrolysis, we will get that into aldehyde form. Actually, the first one is called Etard reaction, second one is an alternative reaction. Got it? So please do check if these reactions are also in place. Got it? So as much as the uh, toluene is concerned, these are the type of reactions you need to learn. Okay. Now let's get back to the drill type questions. Check out first one. Sodium in liquid ammonia. This is Birch reduction. So due to Birch reduction, you will get a product like this: double bond with H and H getting added here. Methyl will be here. So that is a final product. Now this is very important to notice. Chlorine in the presence of Lewis acid. See, in the presence of Lewis acid, then it will give you only orthopera direction. So EA's reaction will take place. So CH3 with chlorine here and CH3 with chlorine here. And I told you that only in this case, the major product is orthokind. Okay. Next. Chlorine, if you react that with H nu, so then we can get CH2Cl. If it is one equivalent given, it is CH3Cl for one equivalent. Otherwise, it will form, okay, CCl3 for excess. In case of excess, you will be given like this. So this will be mentioned to you whether it is excess or one equivalent. Okay. Next is Friedel-Crafts alkylation. So if you have CH3 already, one more CH3 will come here at ortho position, at para position, and one more CH3 will come at ortho position. In these cases, there is, para only being major. I told you only two cases where ortho is major, otherwise para is only major. Next. If you treat this with KMNO4, we learned that KMNO4 will make something called side chain oxidation. It will convert everything into carboxylic acid. Chromyl chloride, we just learned that it will convert into an aldehyde form. This is the alternative chromyl chloride form, which will also convert this into aldehyde form. Okay. Next, concentrated HNO3 nitration. If you are doing in excess, see, in the case of excess, then you will get nitro on all the positions, everybody. Okay. And this is called as TNT. It is an explosive which is called trinitrotoluene. Okay, TNT. If you add excess, if you don't put excess, then you will get only at one position. Either you will get at ortho or you will get at para. And you know that between these two, ortho is major product. This is major product. Ozonolysis. When you perform ozonolysis, see, we have CH3 here, double bond, double bond, double bond. Now, how do we break it? We'll break the bond here, break the bond here, and break the bond here. Okay. So we will get this part and this part, correct? These two parts as uh, 2 moles of glyoxal. This is glyoxal. And 1 mole will be CH3, C double bond O, C double bond OH. Okay. So as long as you are using zinc, only reductive ozonolysis will take place. And these are the products you will report. H2 by nickel, it is a reduction. At high pressure, it will undergo reduction. And this is the product you will get. N-bromosuccinamide, NBS. Okay. N-bromosuccinamide. Okay. So that is specifically used for mono substitution on alkyl group. So that is a product you will get. SeO2. Okay, selenium dioxide will convert again this into an aldehyde form. No mechanism here, just remember it, that will convert into an aldehyde form. Excess in the presence of H nu, here it is given, see, excess is given, so you'll go for CCl3, which is followed by calcium hydroxide, so that will convert into calcium salt. So COO twice and calcium, this is the final product. Carboxylate product you will get, that is the final product. Got it? Right. So quickly go through the reactions one by one, everybody. Check all of them. If you have any doubt, any mechanism issue, anything you want to discuss in detail, please let me know. Sorry. Once you have a plus charge on this epoxide group, then let's say this is toluene. And from the para position, it will always attack on the more substituted side. As it attack on more substituted side, we will get here as carbon attached with O minus. That O minus will become OH eventually. Sorry. And AlCl3 will come out of it. This is the final product. Clear? Next. If you have OC double bond of CH3, I told you OC double bond of CH3 is donating group. Okay, moderately donating group. So moderately donating group will go for OP directing. So we will get this as O C double bond O CH3 with bromine at para position and OCOCH3 with bromine at ortho position. And para position, you will have major. Ortho position, you will have minor product. Please check. Please let me know if you understood these two cases. Done. See the fifth case now. We have NO2 plus BF4 minus. Now, look out for the activated ring here. See, there are two benzene rings. One is this one is this one. Now, the lone pair from here can activate this benzene. Methyl from here also can activate this benzene. While here there is a mild activation from this end, but it is strongly withdrawing from the other end. See, so overall this ring is deactivated and this ring is activated. And within the activated ring, if we have to do nitration, NO2 plus substitution, we have to do it either ortho and para position. Para is already occupied. So where we need to do? We have to do at ortho position only. So let me write down that like this. With N, we have C double bond O like this. And I will add NO2 at this position so that it can have less crowding. A methyl here, and this will be the final product. Correct? This is the major product. So you need to always check out for the most activating position. Next, here also, the lone pair present on nitrogen is donating, while here sulfonation is always withdrawing. So this is deactivating ring, while this is activating ring. So on the activating ring, para position is most open for substitution. So NO2 will be here with N methyl with SO2 connected with benzene, right? So this is the final product. Next, I have phenyl in excess. So first we will get PHC plus charge here with Cl, sorry, with Cl and AlCl3, AlCl4 minus. That's how electrophile is prepared. So the first benzene ring will attack on this position. So you will get benzene with two phenyl groups here now with chlorine. Okay. Again, this will react with AlCl3, generates one more carbocation here like this. And this carbocation, when you react with one more benzene now, it will attach on that carbon. So we will get this as CH with two phenyl rings on it. So three phenyl rings. This is a very standard JEE question asked, degree of unsaturation of the final product. So degree of unsaturation in the final product is how much? We have three benzene rings. Each ring will offer 4 degree of unsaturation. So 12. So 12 is a degree of unsaturation in this case. Clear? Next. FeBr3. Now you notice that bromine, because bromine is already having a lone pair and it will have a double bond character, you will not be able to generate Br plus here. And if Br plus does not come, no reaction will happen here. Neither we cannot remove the Br minus here and plus charge here because of the double bond character, because of which no reaction will take place. Alkyl halide, that means Friedel-Crafts reactions cannot happen on vinylic positions and phenylic positions. Let me explain you. Suppose if you have a benzene and you are reacting with chlorine here in the presence of AlCl3, no reaction. If you have chlorine here in the presence of AlCl3, no reaction. But if you have chlorine here, allylic position, in the presence of AlCl3, definitely the reaction will happen. Allylic group will attach. Okay. So Friedel-Crafts reactions will not happen on vinylic and phenylic positions. Next. This is benzylic position. It's a very favorable position. So here definitely positive charge will come. So check out, we have benzene here connected with these two groups. I'm writing this one. This carbon is this one. Next carbon is this one. So this carbon is a part of a benzene ring here. So I'll write it like this. This is a part of benzene ring. And on that we have a methyl group. So CH2 plus. Because if I remove that chlorine, you will get CH2 plus. So this is a most favorable position for attacking and making into a cyclic structure. So what do we have? Here we can see 1, 2, 3, 4, 5, 6. 6 carbon ring can form. Hence, we can get benzene like this with another 6-membered ring and another benzene group here like this. So this is the final product. Okay. What is the degree of unsaturation, everybody? 4 plus 4 are benzene rings and 1 at the center. So total 9. That is the degree of unsaturation in this case. Okay. Next, in the presence of H plus, you know that wherever there is a pi bond, there H plus will get added, positive charge will come following Markovnikov rule. Well, here there is nothing to follow because it is in a uniform double bond. Then benzene will attack on it. Hence, we will get benzene connected with a 5-membered ring like this. That is a final product. Next, HAOCl. Now, if you come, there are two things that are competing here. One, outside pi bond is competing and benzene is also competing. That means benzene is also trying to take Cl plus. Pi bond is also trying to take Cl plus. Okay. Generally, if you compare the reactivity of pi bond, outside pi bond, general pi bonds, and benzene pi bond, then if I compare the rate here is R1 and R2, then I can say R2 is way, way higher than that of R1. So general electrophilic addition is very strong because see, when it comes to benzene, if it go for aromatic electrophilic addition or substitution, it has to go through the loss of aromaticity. Aromaticity has to be lost. So it will not take that chance. So outside pi bond will be the most favorable to attack. Hence, the product formation will be like this. So this phenol will be this way. And here we will see chlorine getting added, positive charge will come here. And then on that, we will get OH getting added. We'll get chlorine and OH being added. So that is a final product. Got it? Everybody understood? Right. See 12th and 13th now. First, it is an anhydride. Anhydride lone pair will first attach on AlCl3. That makes this particular carbon C double bond O available. So from the para position, it will attach. So first product will be like this. Benzene, which has an ethyl group on it. On para position, we'll have C double bond O. And how many carbons we have now? We have 1, 2, 3, 4 carbons. So this is 1, then I'll write it like this, 2, 3, 4 carbon. On fourth carbon, we have C double bond O, OH group. This is the first product. Then zinc mercury amalgam will always reduce the ketonic part of it. So let me copy that. We need to reduce the ketonic part. So ketonic part will convert into CH2. So H and H. So alkyl part will happen. Now PPA. Now here is what I'll write that reaction. Everybody notice how the PPA works. See, here we have a benzene ring with how many carbons? Notice 1, 2, 3, 4. 4 carbons we have. So we have 1, 2, 3, 4. Fourth carbon is basically an acid like this, OH. PPA is something which will provide H plus, right? Polyphosphoric acid. I told you about this before. So lone pair will take H plus on it. And then we will get double bond O and OH2 plus. OH2 plus will leave very easily. And thereafter, we will get benzene with 1, 2, 3, 4, 4 carbon, which has double bond O with a plus charge. So from this position, it will attack on it. Thus, it will become a 6-membered ring here also, like this. So this is the 6-membered ring which is formed. If you notice the degree of unsaturation here, we have 4 from the benzene, 1 from the pi bond outside, which is C double bond, and 1 from the ring structure. So DO is 6 in this case. This is the product. This is the final product form. Okay. Right, everybody. So please check out this question 7 to 12. If you have any doubt, let me know. Please check 7 to 12. Let's do the next case, which is very similar case here. So check. We are using this as an electrophile. So benzene will attack on the acyl position here. So first, what do we have? Benzene here, like this. And then we have C double bond O here, okay, which is connected to benzene on the other side. And because it broke on this side, we will have this as COOH, correct? So just for your understanding, this carbon and this carbon are same. So I'll just mark it down. This carbon and this carbon are same. And this carbon and this carbon are same. Okay, right. So after that, we are making a reduction here. So as you reduce, that double bond will get reduced here. So we will get this as COOH. Thereafter, you are using SOCl2. SOCl2 basically it is used for removing the alcoholic part and substituting that with chloride. So COCl. This is what you will get. This is the next part, SOCl2. And with anhydrous AlCl3, acylation will happen. So again, you will get the ring size like this with a double bond O. And this double bond O is again reduced by zinc mercury amalgam. So we will get this product. Now listen, by chance if I give you further reaction, that is selenium and heat, in that case what do we get? We'll get anthracene like this. Anthracene will be like this. This is anthracene. Actually in JE it was asked up to anthracene. Okay, clear? So it was also asked like anthracene, you get a product which will have a lesser resonance energy than its isomeric part. Which one will be isomeric part of it? Isomeric part will be phenanthrene, like this. This is phenanthrene. Phenanthrene. So phenanthrene is the isomeric part of it, or isomer which has higher resonance energy. Okay, clear? This is about the 13th. So about 14th one. You're reacting with HF. HF usually makes an Markovnikov addition. So we would get something like this. We'll get benzene, which has group like this with hydrogen getting added, positive charge coming here. Now count the number of carbons from here. You have 1, 2, 3, 4, 5, 6. 6 carbons here. So that 6 carbons will make a cyclization. So we'll get 6 carbon cyclization here. On the carbon where it got cyclic structure, we have 2 methyl groups. Adjacent to that, we have another methyl. So this is the final product. This is the product. So if you see the numbers, so we have this as 1, 2, 3, 4, 5, 6. The same way 1, 2, 3, 4, 5, 6. Okay. So that is a product formation. Got it? In this case, the question was asked as how many number of primary alpha, sorry, 1 degree alpha hydrogens are present. Okay, so 1 degree alpha hydrogens are present. You know how many of them are there? So number of 1 degree alpha hydrogens include 1, 2, 3. 3 carbons we have, so total 9 alpha hydrogens we have. This is the kind of question J has asked. Okay. Next. CCl3 is a very strongly withdrawing group. So because strongly withdrawing groups will not give you Friedel-Crafts reaction. So no reaction in this case. Okay. But chlorination can happen. So chlorination will make it CCl3. and will give you only meta position. So Cl will come here, 100% product will be meta direct. The next one, just so next one, if you notice, this is the same reaction here, like this. We have benzene and benzene. Now, H plus will form at this position. So positive charge will come here and cyclization will take place. So this is one cycle. Like this. This is the other cycle. So this is the final product what you will get. Okay. Set. Next one, if you notice, with NH2 concentrated HNO3 H2SO4, when it comes to nitration of this group, as I told you about this one already, we will be learning this multiple times, so don't worry about it. As of now, just remember nitration happens at ortho, para, meta, all three positions. NH2 with NO2 here and NH2 with NO2 here. This will be only 2%, this will be around 47%, and this will be around 51%. Para will be the highest. And significant meta will come because you are pushing this in acidic medium. In acidic medium, nitrogen will take H plus and becomes withdrawing group. That's why it will facilitate meta position. Okay, next one. Third butoxy group here. See, I told you about this. This is the limitation of the Friedel-Crafts acylation. That is C double bond O Cl is there. If you treat this with AlCl3, first you will get C double bond O plus. Okay, plus AlCl4 minus. Got it? And then this group will be unstable form. I mean, it will try to become more stable by releasing carbon monoxide gas from here and convert into a 3-degree carbocation. So hence, if you are treating that with methyl here, I mean toluene here, so basically you are directly reacting with this carbocation form. So the product what you will get here will be methyl, and here you will get tert butyl. This is the final product. This was used as a drawback of one of the drawbacks of Friedel-Crafts reactions. Next one. This one is called Riemer-Tiemann reaction. We have a lot to discuss about this in the next upcoming topics. All right. So here it is just to give you the reaction name. You will get aldehyde form on ortho position. This is major product. And the name of this is salicylaldehyde. Salicylaldehyde. Okay, don't worry about it. We'll be coming across this reaction with all the mechanism part going here. Next. Now, notice here, the reaction is like this. We have carbon with 3 methyl groups. Then we have CH2Cl. And when you treat with AlCl3, first you will get a carbocation here. Thereafter, methyl shift will take place. On making a methyl shift, you will get like this with a positive charge on it. And that benzene, when you attach on that, you will get here as 2 methyl groups and this one. So this is the product you will get. This is the product we will get. Next. In the presence of FeCl3, I told you that no rearrangement will take place. Because carbocation, fully formed carbocation is not formed. So this will be the final product. Final product, no carbocation formation. In the case of AlCl3, you will have carbocation formation. In this case, no carbocation formation. Okay. So, right, quickly check out this reaction from 13 onwards. First check all of them. Quick, 13 to 18. Next set of reaction. In case if you use AlCl3 and HCl, this is called an isomerization reaction. Isomerization. So basically, it will remove the methyl group from one position at CH3 plus kind of a group, and then it will make a substitution on that. Okay. Sorry, CH3 minus kind of a group and substitute on the other side. So that's why you'll get this as CH3, CH3, and another one which you can get is CH3 and CH3. These are the products you will get. Okay. So positional isomers is what you will get. Next. Here, first you can notice that there is a carbocation forming because it is at allyl position. So when you have it allyl position and react with AlCl3, that chlorine will go away and carbocation will form like this. Carbocation will form. The carbocation can show the resonance stabilization like this with plus charge. Okay. And now you can see this is the isotopic carbon. This is the isotopic carbon we have. That means the benzene can attack directly on this position or it can attack on this position. So chances are you'll get 50-50% of both. So you'll get a double bond here like this. And you can get double bond here like this, in which this could be carbon 14 or this could be carbon 14. So chances are 50% of this product and 50% of this product. Next, when it comes to pyridine, just now we learned that beta position is more stable. So NO2 major will be forming here. Okay. Now this is a very interesting reaction. See, how does this proceed? CHCl3 in the presence of OH minus KOH will give you CCl3 minus, and CCl3 minus generally is unstable because of the chlorine repulsions, as all of them are on same plane. So all these chlorines are on the same plane in a pyramidal structure. So they will repel and give CCl2 plus Cl minus. And now this is the electrophile that is being generated. So electrophilic addition will take place here first. So that means on the double bond here, you will get C Cl Cl addition. The pi bond will get added like this. And because chlorine is a good leaving group, so what would happen? Here, this bond will try to expand. This way, the ring expansion can take place and push this chlorine group away. Now it has become a six-membered ring like this. Okay. And in that six-membered ring, here we get chlorine 1. And adjacent to that, we have a positive charge. Then we have a double bond here like this. This is the product you got. And a double bond has formed here. Now see that positive charge which is there can take away this H plus by resonance, because double bond can shift here, positive charge will come here. From that positive charge, H plus can be removed to make a double bond. So that means we are getting basically a pyridine again. So we'll get pyridine like this with chlorine here. So this is the final product. Okay, so beta chloro pyridine is what is the final answer. It's a very special case, so do remember that. In the case of methoxy group OMe, you will get bromine at ortho position and bromine at para position. Okay, and you know that this is the major product which you will have. Okay, this is minor product. Bromine water. Now listen, bromine water will make the substitution strong at all three positions, all two positions here. But here is an interesting fact. SO3H in aqueous solution, we learned it get desulfonated. So which means Br will be here, and again H will come plus SO3. And since the solution is still in bromine water, again bromine will attack on it, and you will get tribromo group once again. So you'll get Br Br and Br. You know that this is 2,4,6 tribromophenol. Tribromophenol. 2,4,6 tribromophenol is a white PPT. Okay. The same logic applies to nitration also. If you have concentrated HNO3, you will get nitration done on all the positions. So first you will get this COOH is there. Carboxylic acid in an acidic medium, COOH, will undergo decarboxylation. So H will come here, NO2, NO2, and OH will be present here with CO2. Now this, when it reacts with concentrated HNO3 with concentrated H2SO4 once again, one more nitration will take place. In fact, you will report the final product as this one only. This is the final product you will report, and this is called picric acid. This is picric acid. Phenol with CS2, here you can see CS2 because COOH is occupied, we can get only one bromine that is not in acidic condition. The second step is acidic condition, that means H plus and H. This time decarboxylation will take place. So then only monobromo product will be formed with CO2. That is a final product. Okay. Next. Aniline with Br2, we have already learned that, Br, Br and Br will come at all three positions, right? Even with bromine water also, NH2 is so strongly donating that it will give Br at all three positions. So same product will form. Okay. In fact, to stop that only, we'll do this reaction, the next reaction, which is about, first, when you react with anhydrate, we'll get NHC double bond of CH3. This is acetylation. The name is acetanilide. Acetanilide. Next, then we do nitration. As you do nitration, we will get NHCOCH3. Nitration will happen at this position. And thereafter, when you remove, again you do hydrolysis, basic hydrolysis, we'll get NH2 back and NO2 will be present here. So with CH3CONA. Okay. So you can see this time we are managed to get only mono substitution. So if you want to get only mono substitution, then you have to convert first aniline into this form. Then it is possible to get mono substitution. Then just now we discussed if you have chlorine and NO2, in that case, listen more towards Cl. So make Br position here. That will be major product. Okay. One second. Next. N2O5 is about nitration. So this group, ether group, does not do anything, but you'll get nitration. So in para position, you'll get NO2. Naphthalene, I told you that there is KCP and TCP product. So here, when you treat it at 80 degrees, you will get alpha position, which is KCP, kinetically controlled product. If you go about 160 degrees, now that is TCP, so SO3H will form at beta position. That is thermodynamically controlled product. Next. This we already discussed, whether if you have any biphenyl system, only para position is the most active position. So therefore, bromine will always come at para position irrespective of donating or withdrawing group. That is activating or deactivating groups. Always it will come out at para position only. OME. Okay. SiMe thrice, this will easily relieve out from here and gets H plus from here with OH, and this will convert into trimethyl silicon plus and ClO4 minus. Okay, correct. This is a product formation. Next, OMe with nitration here. So you see that OMe will form and nitration will happen at this position because SO3H in H2SO4 will get desulfonation and NO2 will come here. If excess is given, if excess is given, then we know that NO2 will come at all the positions. So NO2, NO2, and NO2. So it will come at all the positions. Got it? Right. So quickly go through it once. Everybody, check out. From 23 onwards, please check till 28. These three, in fact, this one we have already discussed. So here, Birch reduction, OMe with double bond with H and H because it is a donating group. Bromine, which is a withdrawing group. So Birch reduction will make double bond here. Sorry, double bond here and here. H and H addition happens here. This is donating and withdrawing group. Okay. Next one, BF3. When you make a treatment with this one, chlorine will go away and fluorobenzene will make para substitution. So from here, you will get benzene like this. So this is the product you will get. Plus BF3 and HCl will come out of it. Clear? Last, when it comes to bromine will, there are, this is withdrawing, this is withdrawing, this is donating. So you should always look with respect to the donating group. So NH2 being donating group, NH2 will be here. Br, because other ortho and para positions are occupied. So you can't use that. So there is only one location. So this is where you will get, that is major product. That's it. So these are the products, guys. Okay. These are the four last cases which you need to learn. Correct. So more or less, I have covered all the kinds in this assignment.